Hello, my name is Kevin Butterfield. I'm the director of the John W. Kluge Center at the Library of Congress. That's a center for research and scholarly programs that the library has. And since the year 2011, the Library of Congress and the Kluge Center have been partnering with NASA on the Baruch S. Blumberg NASA Chair in Astrobiology, Exploration, and Scientific Innovation, where we host scholars and residents who work in the field that we're about to discuss. One of those scholars, our current chair, Jacob Berkowitz, was supposed to be sitting in this chair, and we wish him the best because he's not feeling well this morning and asked me to sub in. So I'm an 18th century historian, excited to talk about. And actually, funny enough, that's not even old enough to be covering some of the things we'll be discussing today, because we're looking back in time as much as we're looking at the present. I'm honored to introduce Nathalie Cabrol, explorer and astrobiologist, the director of the Carl Sagan Center at the SETI Institute. She researches life beyond Earth, develops science exploration strategies for NASA, for Mars and Titan, among other efforts. And today she'll be talking about her brand new book, The Secret Life of the Universe, an astrobiologist's search for the origins and frontiers of life. Sitting to her left is Dante Lauretta, who directed the team that collected samples from an asteroid, offering profound insights into the solar system's formation. Lauretta's research spans the solar system's origins, Earth's habitability, life's origins, and the connection between life and consciousness. His new book is titled The Asteroid Hunter, A Scientist's Journey to the Dawn of Our Solar System. Please join me in welcoming both of them. Thank you. I mentioned the term astrobiology in my introduction because we have a chair at the Library of Congress devoted to this work. You both work in this field. How do you define astrobiology? Nathalie?
Broadly, this astrobiology is the search for life, not only beyond Earth, but also using the search we do outward to look back at the Earth and try and understand where we are coming from.
Dante, how would you flesh that out as well?
Yeah, I think it's a new word for a lot of people, and I always say you probably have heard of astrophysics, which is the study of physics applied to the universe. Astrochemistry and astrobiology kind of follow in that vein. We take the principles of biology and we try to understand how did it start and where is it in the universe, and really what is it? When you get into astrobiology, you get down to the point where trying to define life is not as easy as you might think. So it really is the study of biology applied to the cosmos.
Dante, let me stay with you for a minute because I mentioned a mission to an asteroid. I actually have a sheet of stamps that honor this mission, but most of what I know about it come from that stamp, which is not very much. I know there's a parachute involved, and so that's where there was. Could you give us the, excuse me, the short version, the elevator pitch for that mission, maybe how you would describe it before it was even a reality?
Absolutely. Yeah, since 2011, I've had the honor and the privilege of serving as the principal investigator, the person in charge of NASA's OSIRIS-REx asteroid sample return mission. We built a spacecraft that launched in 2016, went to a near-Earth asteroid named Bennu, which we chose very particularly because it looked very dark, and we hoped and have now proven that it was rich in carbon and water and represented the kinds of objects that were delivered to the early Earth that made our planet habitable and maybe even delivered the molecules that were essential for the origin of life. We collected a sample off the surface of this asteroid in October of 2020, left Bennu in May of 2021, and just under a year ago, September of 2023, delivered a capsule with a parachute that finally opened and safely landed in the Utah desert, and we delivered that material to NASA's Johnson Space Center and have distributed it all over the world for scientists to address these big picture questions that we've been discussing.
And start.
Thank you.
Absolutely, worth applause. From concept to execution, how long have you been working on this?
So the book, Asteroid Hunter, really goes through my story. It's a memoir, and I was first brought onto the team in 2004, now over 20 years ago. I was a young assistant professor, and the lab director, Dr. Michael Drake, invited me to be his deputy on the program. And these are long missions, and you're always thinking about the next generation and the handoff, and that's what happened. Unfortunately, earlier than we had hoped, but Mike passed away in 2011, and I took over the leadership of the program then.
Nathalie, I introduced you as being in charge of the Carl Sagan Center at the SETI Institute. Tell us about this, the origins of that program, actually, and your beginning of a search for better understanding life and its origins in the universe.
So the SETI Institute was founded this year in November. That will be 40 years. And Frank Drake, you all heard of the Drake equation, which is to try and find how many potential extraterrestrial civilizations there are in the Milky Way. So Frank designed this formula that tries to understand this number, and in doing so, lined up all the factors that you need to figure out this number. And when you look at the formula from the Drake equation, it's basically the first astrobiology roadmap, because you need to understand what kind of stars are good for planetary systems to form around, and how many of those planets around those systems are going to be habitable for life as we know it. And then among those, how many have actually an environment that's favorable for life. And in those, how many develop life, and in those, how many develop advanced life and technologically advanced civilizations. And then the L factor, which is how long those civilizations still emit some signals that we could perceive. So that's how the Carl Sagan Center was born in astrobiology at the SETI Institute, and astrobiology broadly, which is the origins of life to extraterrestrial civilization. And how I was brought in this, so, well, just like you, it goes away back then, but I became the director of the Carl Sagan Center in 2015. I am also an astrobiologist, and that was part of the deal. I said, I have too many ideas I still want to explore. I don't want to do any administration, so I'll do the strategic vision. I'll keep doing my research. That's the deal. You live in it, or not. And I was fortunate enough to have a CEO who was very understanding, so here I am, both directing the research and doing my own research.
And much of this research you lay out in the book that moves from Earth to far beyond. I wonder if you could just, because this book covers possibilities for life both near and far, and by near I mean Mars and Venus, but also it's extending outward, as you said, the Drake equation, these ideas of trying to understand how much life may be out there. Could you just pick a place? Obviously, Dante's got an asteroid. Can you pick a place and tell us a little bit about the quest, the search for life as you approach it? Pick a place.
Well, pick a place. It's just like asking parents who have a number of children to pick the one they favor, Do it. They all have their personalities, right? You could say Mars, because we have been there a long time, and Mars makes us dream through science fiction, and now through science, because, well, the science fiction we know is not there. We don't have crystal domes on Mars. But there is a fundamental thing about Mars, is that the closest we ever had to the Earth, and the record of our own history on Earth, so early, the transition from prebiotic chemistry to life is erased, pretty much. There is very little chance we'll ever know from an outcrop on Earth where we are coming from. That's why Dante is going after those asteroids, because they might hold that clue, and we're going to Mars because maybe in this old 4.3 billion year outcrop, we might have that transition somewhere. So Mars is good for that, but then you have the outer solar system. That's for present life, where we might be looking for something that's present, that's alive. Titan, name them. They all have something. So I'm not choosing. I'm sorry.
Okay. Dante, Nathalie mentioned looking chemistry, trying to find something there. And you touched on this when you briefly described the mission to the asteroid. What exactly have you been finding, or were you hoping to find?
Yes, the samples are an astrobiologist's dream come true, in the sense that they're very wet. They formed, looks like when rock interacted with water, in a very similar manner to the hydrothermal vents that we see on the ocean floor on Earth. These are rocks dominated by clay minerals, and clays are distinctive because they can hold water in their crystal structure. And this is important because we're trying to figure out how the water got to the Earth The Earth formed early, it was very hot, there was giant impacts, lots of volcanism. The water and the carbon probably came from the outer solar system, and we think that this asteroid represents that kind of sample. It's very rich in carbon, and the carbon chemistry is very diverse. Lots of organic molecules. We're seeing the kinds of things that are used in biology. For example, the letters of the genetic code, we call the nucleobases. There's 5 that are used in biology. We found all of them in the asteroid sample. Amino acids, which make up our proteins, we used 20 of them. We found about 13 of them in these samples so far. And we're finding these globules, we call them organic nanoglobules. They look like little vesicles with carbon-rich shells, kind of the first stages of origin of life in a process we call encapsulation or compartmentalization, where you have to separate a chemical environment from the surroundings, and that looks like what's happening here. So as Nathalie was saying, we're looking for this transition. How do you go from a rock to something that's alive? That's a really hard question when we really have not made a lot of progress. I would say since the Miller-Urey experiment, we've been kind of incrementally marching towards this chemical basis for this. I hope these rocks got us pretty far along that pathway, and that we know that we're not only delivered to the early Earth, but to early Mars, to early Venus, to the moons of Jupiter and Saturn. So these are the seeds or the building blocks that all the planets grew from, and where the water and the carbon was delivered to these objects.
Nathalie, I saw in your book a reference to this idea that Dante was describing of important components, anyway, of what become life coming from other places. You mentioned Mars specifically. What surprised you about the discoveries that we were able to pull from this asteroid? Or did anything surprise you?
You know,
Maybe
we
it's
still
exactly
need to see their papers, so we're waiting.
First one, hey, the first paper
Well,
came out.
no, I
The first
know.
paper is out.
But you just told me there is more, so
There's
I want
a lot
to know.
more,
Yeah.
yeah.
So the thing is, and this is really what Dante just talked about, is that the stuff of life is embedded in planets and in moons. It's not that there is a strike of a magic wand. It's all right there. So now we have to think, does it take only to have the proper environment for that stuff to, transition from prebiotic chemistry to life? But then again, where do you draw the line? Mm-hmm. Because if it's really a transition, where do you draw the line between living and non-living? And there are people right now who are actually pushing on that idea. And so, anyways, this is to me the one of the biggest, not even challenge, but fascination about astrobiology at this point in time is that we are pushing back that idea of not pushing back on, but pushing back the point where we are going to say something might be alive or not. Mm-hmm. And we are changing the paradigm. We are looking at life in a very different way. Today, we don't have a good definition for life. We have a working definition for life. So interestingly enough, we are going after something we don't know what it is about, but it doesn't matter. What matters is that we are setting ourselves. We are just moving forward and trying to understand what it is, because as we go, and with the kind of rocks that you're bringing back, then we're articulating different questions, and we are understanding things differently. So, science is a process.
You mentioned learning about ourselves. Both of you, although it sounds like you can stay away from the administration and details of it, but both of you work in very large and in some ways global efforts, right? You're part of a global scientific community that's exploring these matters, but also you've been parts of teams I'll start with you, Dante. What did you learn about that work, the team element of the endeavors that's necessary here?
Yeah, OSIRIS-REx is the product of thousands of people working all over the world to make this dream come true. I mean, it really is magic, and science is how we get it done, right? I remember back in 2004, that first meeting, talking to our aerospace partner, Lockheed Martin, and they were like, you can pick an asteroid, and we'll bring a sample back to your laboratory. And I was like, wow, it's like an amazing kind of concept. And that kind of set the tone, right? What you have to do is you have to build a team. And the team has to be unified. Even though some of us are coming from universities, some of us are coming from industry, some of us are coming from government, different cultures, different priorities, different processes, you unify them into this common vision. We are not Arizona, Lockheed Martin, NASA. We are OSIRIS-REx. That is what we are, and we're all in this together, and everybody is valued, everybody is important, every role is essential to mission success. And I communicated that to the team regularly, how proud I was of them, how we overcame challenges, and the book is full of them. It reads like an action adventure because as soon as you solve one problem, the next one is right there in front of you, and the team has to rally, brainstorm, throw it all on the table, and figure out how we're going to make all these pieces work. And that is what led to the success of the program, is that unified vision and that common team spirit.
Nathalie, tell us about the Carl Sagan Institute, SETI. What kind of collaborations and discoveries about cooperation among humans have you been learning?
Yeah, and the SETI Institute is mostly about people who are doing their own research but come together in teams. I can talk about the work that we are doing in the Andes, for instance, where we have, that adds the element. I've been part of NASA's mission as well, the Mars Exploration Rover, and same thing, we had to pull through, we were the first one doing this with Spirit and Opportunity, so we had to write the book. And when I say write the book, even dictionaries, because you have to have engineers and scientists communicate with each other, and you realize that you are saying the same words, but they don't mean the same thing. And it could be really challenging and put your mission at risk. But within a few months, these are kind of things that are behind you, and this is a family. Astrobiology is excellent in that too. It's because it's a multidisciplinary science. And then you are asking a question, and you have somebody coming from biology, somebody coming from geology, somebody coming from the robotics or from environmental sciences, and they all have different responses or views about that question. And when you put this together, you have a hands, vision of what you're looking for. And so that's the magic of astrobiology. When you go in the Andes, like I do, for analogs of planetary worlds out there, you had the element of extreme environment. We are doing science at 20,000 feet and diving into lakes that are that high. So then on top of that, you have to have the trust. Well, you do have to have the trust in your team. It's, otherwise you wouldn't have your team members with you. But there is a real physical life and death elements that's added to that. So something that is often not very well perceived from the public is that when you do this kind of science, there is really an athletic component and a challenging component when you have to climb mountains at 20,000 feet and then get rid of your mountaineering gears to don a suit. Have you tried to don a suit at sea level? You know what that is. So try at 20,000 feet when you have half of the atmosphere to breathe on.
Yeah.
So, and when people ask you why you're doing this thing, you say, well, I needed samples.
You've also mentioned extreme environments on Earth. Could you tell us a little bit about what you've been learning here on Earth that's relevant?
Absolutely. So there's a couple examples. I was part of the Antarctic search for meteorites in 2002, 2003, and this is an annual program. Antarctica turns out to be a great repository of rocks from outer space. It's a desert, so they don't rust or weather away, and also the glaciers kind of bring all the rocks that have been falling across the whole continent to the base of the Transantarctic Mountains. And that was a really profound expedition for me because up until that point, I'd been studying meteorites and trying to answer these questions, especially about organic molecules and delivery to the Earth by studying those kinds of samples. And there was a day out in the field, it was a warm day in Antarctica, sunny, and meteorites are black rocks. And the meteorite started melting the water, the glacier water that was around it, and it was sitting in this little pool. And my colleague, Danny Glavin, who's at NASA Goddard Space Flight Center and my organic analysis lead, he was with me and he looked at it and he's like, dude, that rock is exchanging amino acids with the water right now in front of our eyes. And I was like, you're right. And I say this in the book, and I was like, it was like finding a treasure and then finding out it was all counterfeit. It was like, how are we going to answer these questions? Because these rocks, as soon as they get on the surface of the Earth, they're contaminated and biology takes over. And that was when the light bulb kind of went off and I was like, we're going to have to go to an asteroid and get a sample.
And it worked.
And it worked.
It worked.
20 years later.
We're going to go to questions from you quite soon, so give me 5 or so minutes, and then you guys can start walking towards microphones. There are a couple of different aisles that have microphones. I'm excited to hear the questions that you have. In all of this, Dante, I'll go back to you quickly. You've, particularly because your book is very reflective of your own better understanding of yourself, your thinking about not just the existence of life, but what your existence is, what human existence is all about. Tell us a little bit about the inward journey that you've experienced over the last 10, 20, whatever years.
Absolutely, yeah. My inspiration goes back to SETI and the Drake equation, actually. As an undergraduate student, I got a NASA space grant research internship, and it was the early 1990s, and SETI was actually funded by NASA, called the High Resolution Microwave Survey. And that just fired my imagination and my inspiration. It really got me thinking about thinking. And it was like, what are we looking for with SETI, right? We say we're looking for technology, we say we're looking for biology, but we're really looking for a mind, something that's thinking out there like we are, like we imagine everybody else is. And that is what's driven a lot of my work lately. It's like, how do you go from rocks to life to thinking, to a mind that has this internal world we call consciousness? And a lot of my work today is trying to figure out how those things are connected and what is it about the fundamental nature of the universe that allows that to happen. And I just want everybody to stop and think about it, right? Our standard neuroscience model is we have these cells, we call them neurons. They send electrical signals and they send chemicals across cell membranes. There's trillions of them, and somehow us arises from that. Our individual identity, our thoughts, our inner world, however you picture the universe, all of that somehow arises from this collection of matter, and we're looking for other similar collections in the universe that are going through the same process. And you get to the bottom and you realize we don't know really at all what is going on. And that to me is so inspirational and so profound that I'm going to continue to pursue those more cutting edge kinds of areas of research.
And Nathalie, this is at the heart of your work, right? You write in the book, this comes from one of the later chapters, our generation is living through a unique moment in time when humanity has just enough knowledge and technology to begin searching for life beyond Earth. Could you flesh that out?
Well, we have been dreaming and we have been thinking about those questions forever. I suppose, are we alone is as old as humanity. But right now, we are starting to have the spacecraft. We are starting to have the technology and the instruments. But interestingly enough, and I think this is our generation of scientists, that's why we're coming back to those questions, is that, well, we are looking for life and we don't know what life is. We are looking for other intelligences. We don't know what intelligence is. And we are looking for, as you said, another neural network somewhere. And we don't know what consciousness is. And we have been going, at this question for a long time. We don't have the answers. Science is not bringing the answers right now, but it's just helping us to understand what the question is and maybe articulate it a little better. But what is really interesting is that we are starting to push back on the most fundamental ideas that we had in the past generation. The latest one, I don't know if you've seen that, Dante, is those cosmologists and physicists and neuroscientists are starting to go after the notion that consciousness is a function of the brain. And they are connecting this with quantum physics. So if we thought that consciousness is a function of the brain, so the great humans, we are the one gifted with consciousness, that wouldn't be the case. It just means that we're not talking about beings having consciousness, no, not consciousness. We're talking about levels of consciousness. Everything that's alive is conscious, and maybe more. So these are the kind of things where astrobiology is literally pushing the boundaries today. And that some people might say, well, this is what's in my ancient text, or it's in the spiritual book. Well, guess what? It's because there is no separation between spirituality and science. They are just two different ways of looking at the same question, you know. I often say that science is a way to measure nature, and intuition and spirituality is a way to understand what we cannot measure. So I would say, you know, and for me, you say that you're looking to those conscious. I told you I am questioning the questions, and this is what I'm doing, and you too now, because we are coming after a few decades of research. But what that did to me as well was sitting on top of these big volcanoes, you know, looking at trying to understand Mars 3.5 billion years ago. One morning I woke up and I said to my husband, we're preparing to dive, and I said, you know, this lake and this volcano, they have been telling us about Mars 3.5 billion years ago, but they're also telling us about Earth right here, right now. And what astrobiology does is that it teaches you about life, about environmental thresholds, and about how fragile habitability is. And since that time, you know, I really clearly understood that we had this great mirror to ask questions for ourselves, to understand our place on this planet, but also the tools we develop for planetary exploration and astrobiology. We can use them to look back at the Earth and try to better take care of it. So I think that you can see this in Dante and me. These, you know, there is no separation again. It's not because you're looking far away into the cosmos. In fact, you are looking deeper inside of you. So that's the beauty of astrobiology.
That's right. Very well said.
I want people to begin moving to the microphone if you have a question. But Dante, while they're doing that, if you could reflect on this idea of a deeper understanding of the fragility of life here on Earth.
Yeah, it's an interesting way to phrase it, because life is very robust. What's fragile is humanity, our civilization, and the biosphere we enjoy. I don't worry about life going extinct, because there's organisms that live 3 miles down in the crust, and they don't care about what the climate is doing, right? But is that what we want, right? It really becomes a little bit selfish in the sense that we want a planet where we will thrive, where our children will thrive, where our descendants will thrive. And there is something very special happening with humanity. I mean, our level of consciousness is distinct. I agree with Nathalie. I think everything that's alive has some level of consciousness, but ours has reached language and culture and art and music and beauty and all these things. That's reflected in some cases in the natural world, but we've taken it to a whole new level. That is what is fragile, I think.
Let's start here to my right.
Hi, my name is Ishara Laxina. I am 9 years old, and my dream is to become an astronaut when I grow up. Miss?
Go for it, girl.
Miss Dr. Nathalie, what is the definition of life to you in general or in space?
Ooh, that,
Define
you know,
life.
as I said, this is a great question. As I said, we don't know what life is. What we know is that we are here together and we are sharing those ideas. So life is something special. It's different from a rock. It has feelings. I find you beautiful.
Thank
you know? And so there is this perception that life can look and understand the universe around around us, and interact with each other and have feelings about it. So, you know, for now, it's what I think about life. In outer space, I don't know. You know, what I know for sure is that if there is a different species somewhere out there, they, like us, will have evolved in an environment, and who we are is the product of this evolution of life and environment for the past 4 billion years. So they will be very different. And you know what? That's really cool, because that gives us a different aspect, a different vision of the beauty of what they feel, you know, about life, what life can be. So I don't know, but it's really cool, and maybe you will find the answer becoming an astronaut.
Wonderful.
Thank you.
So cute.
We'll come to my left.
Good morning, everybody. Really looking forward to reading both of your books, which I got this morning. My question is for Dr. Lauretta. It was an amazing experience to be able to watch the NASA live stream of the mission return in the Utah desert. There are many reports, papers, interviews coming out or that has already come out as a result of the mission. When did you start having the idea of writing a popular nonfiction book about your experience, and how did you start deciding the scope of that story as you put pen to paper?
That's a great question. It's several questions. I really started putting the concept together in 2018, just as we were about to arrive at the asteroid. And you're kind of getting yourself ready for this big adventure, and it was awesome. I mean, it was just, we were at another world, and every day I was looking at pictures coming down. And I really thought about how lucky I was to be in this position, how fortunate I was, how all the people who had helped me before, my mentors, the pioneers of astrobiology and SETI, like Carl Sagan, Chris Chiba, who I always looked up to, and I was like, I think there's an important message here that, I came from a very disadvantaged background. I was the first one to go to college in my family. I wanted to give that inspiration. And I also, when I first got attracted to SETI, I was discouraged from studying it by my senior professors. They're like, it's a career suicide, it's a dead end, don't do it. And I want to break that wall down. I was like, no, it is a great topic. We need to be thinking about this, and I want to enable people to really think about that. And then in terms of the scope, I probably wrote 3 times as much as is in the book. And then you're like, okay, that's good because you can throw away all the junk and pick out the jewels and make the story really start to sing. And it was a process. I worked on it for about 5 years or so to get it down to where it was, except for that last epilogue, which I wrote in the hotel room in one night in Houston as we were processing the sample, because that's the final conclusion of the story.
That's great. Thank you.
Yeah.
Another junior scientist.
Here we are. Are you ready?
How long did it take to get from Earth to space? Wait, no, to the asteroid.
To the asteroid. Thank you. Good question. So we launched in September of 2016, and we arrived in December of 2018. So that was 2 years and 3 months flying through space to get to asteroid Bennu.
And how fast would it have been flying at its peak?
Well, it's interesting. Velocity is relative. Relative to the Earth, it's about 28,000 miles an hour.
To my left.
Hey, good morning. I had a question about the OSIRIS-REx project. You were talking about you guys are under the assumption that a lot of the water and carbon was delivered here by like comets or asteroids. Why do we then not see similar amounts of water on either the moon or Mars or similar conditions?
Mm-hmm. Good question. The moon is got a very low gravity field, so it would be hard to hang on to that material. There is water on the moon, but not at the levels that we see on Earth. Mars has a lot of water, actually, and there was just a paper that came out a week ago with the seismometer that found oceans worth of water deep in the crust of Mars. Similarly for Venus, we think Venus may have had oceans early on in its history and has lost them through climate change. Similar to Mars, Mars has gone through a different climate change, lost most of its atmosphere, and the water's now frozen. So it does look like water was widely distributed across the inner solar system, and at least the 3 terrestrial planets have gone through very different histories. And there's an important lesson for us in that, because you can be the hot hellscape that's Venus, you can be the dry, arid desert that's Mars, or you could be this beautiful oasis that's the Earth. And we need to pay attention to that because we want to keep it this beautiful oasis, and we don't want to be a pizza oven or a deep freezer like Venus or Mars, right?
Thank you.
Yep.
Natalie, in your book, you mentioned the outer solar system too. Dante kept us quite close, Mars and Venus. Could you tell? You mentioned Titan. I know there are other moons out there.
For?
Water.
Oh, for water. Europa and Enceladus is throwing its ocean literally in outer space. So we know it's there. We also know from the chemistry that some of the minerals had to be formed at least 50 degrees C. So there is some form of heat, which is not surprising because you have these big giant planets like Saturn for Enceladus, which pulls and pushes on Enceladus. And so you have friction and you're creating heat. So you have lots of water there, but the mind-boggling things are, Ceres and Pluto. We're talking about that. Titan is just this incredible thing, because it's much too cold out there to have this ocean of liquid water at the surface, but you have hydrocarbon lakes and seas at the surface of Titan. And if it's not mind-boggling enough, 20, 50 kilometers down, you have a water ocean. So what I really would like to see is where those two meet and what kind of chemistry we can have.
Absolutely.
So yeah, water everywhere, methane everywhere, but water is really everywhere.
Sir.
Good morning. My name is Lou Evangelista, and I want to thank you all for making me love asteroids. I used to be afraid of them, but now I wouldn't be here if there weren't asteroids. So thank you so much. And also, you have the same questions I have, but you've got the smarts to answer them. And all I can do is keep asking. One question I have is, in your search, how do you prevent yourselves from falling into the anthropomorphic bias of the definition of life and of just the other beings? They're not like us, right?
Listen, this is a great question. And yes, this is the most biased experiment for a number of reasons, because we only have one data point, and that's us. And plus, we are the observation and the observer, the experiment and the experimentator. So that wouldn't fly for no PhD, I know, all right? But this is what we have. And it doesn't matter that we're biased, because if you take the mediocrity principle, we're here, it's working, and we might be representative of a large population. That's the mediocrity principle. And on top of that, we know that the stuff that's making us, that this gentleman here now knows a lot more about, it's very common. It's everywhere. And it's not a surprise that we are made of that stuff. And when you're looking at the ingredients that life as we know it, that's the bias, needs. It needs water, plentiful, energy, nutrients, a shelter, and a source of carbon. So, there might be different biochemistries, but looking for the type of life as we know it is not that stupid.
Hi, so I just have a quick question. You're talking about these organic blobs that are on these asteroids, right? Mm-hmm. Have we, and you talked about like it being a soup and there's some like amino acids floating around there. Have we modeled these, like the environment at which these globs exist and see if any proteins or anything could build, like what the probability is behind that? Has that been modeled, or is it kind of at the forefront of what we're...
That is exactly what we're doing right now, yeah. So
Okay.
we're constraining the fluid environment composition, the temperatures, the pH, the soluble ions that are in there, and the temporal evolution, how did it change through time? And then we're starting to say, okay, when did the amino acids show up? And you mentioned proteins. That is really something we're hoping to find. A protein is when you take amino acids and you link them into a chain. Even two of those linked together in the sample would be a huge discovery, so we're trying to find those. That's the next round of analyses right now, and we just put a large amount of sample into the laboratories exactly for that. So the modeling is getting started,
Okay.
and the chemistry is advancing in the laboratories, and we're constraining the environment. So that is exactly where the program is right now, is to do that.
Okay, sounds good. Thank you.
You will have to report to that gentleman.
Yeah, please, we need help. We need help. Yep.
Hi, this question is for the both of you guys. Earlier, it was mentioned how once the parachute came back with the asteroid sample, parts of it were given to countries and organizations all over the world. Have you found with the changing global political climates and alliances, does research kind of get gatekept or not shared depending on changes, or is astrobiology a field where it stays pretty collaborative?
Great question.
That is a great question. And it's we're starting to see a division in the world, I would say. So we work really well. For example, the prime partners on OSIRIS-REx were the United States, Canada, Japan, and France. And that's a really tight group, and we work really well together. With the samples, we've got people in Australia, we've got people in other countries in Europe. And so that's going really well. Where I'm seeing it's really hard is trying to work with colleagues in China, who are doing a lot of great planetary science and exploration, and we're literally legally prohibited from working with them. So we are seeing that, and I think that always kind of bothers me, because one of the prime missions of NASA is diplomacy. That's why we have this agency. We work with Russia. We did through some very tense geopolitical situations. We should be using this commonality of our humanity and our life on this planet to overcome these political barriers, but they're still in place right now, especially with China.
I would just add something which I found very, very sad. And the latest example I got was somebody from Iran will respond and say, I would really like your book, but my country is under such, political constraint, etc. There is no way. How do you respond to that? Because people are really held hostage of government policies. And as you say, we have difficulties working with China, working with Russia, working with Iran. There are a lot of good people. There are a lot of great minds. And so I find it sad.
Thank you.
Hello, I was just wondering, sorry. Hello, I was just wondering, what sort of led you to believe that you might find these building blocks of life, like proteins, first on asteroids compared to first being created in, geothermal vents near the bottom of the ocean?
That came from the meteorites, especially a very important meteorite fell in Australia in 1969 in an area called Murchison, and meteorites are named after the place where they land. So the Murchison meteorite was where the amino acids were first detected in extraterrestrial samples. And what gave us really good evidence that they were not contamination is that it has a lot of amino acids that are not used in biology. And in fact, that's what we mostly focused on, because we were very sure that those weren't terrestrial contamination. But then you get to the point where it's like, well, we really care about the ones that are used in biology, right? So that's what led to the asteroid sample return concept. It was like, yeah, the meteorites are telling us there's important chemistry going on that seems very relevant to what we call prebiotic, before biology kind of environments, but the signal is getting lost on Earth, so that's what drove us to the sample return mission.
Thank you.
Good morning. Is some of your work looking for exoplanets using telescopes and orbital platforms? And if so, have the instruments now, like the James Webb Space Telescope, made terrestrial-based observation platforms no longer useful, or do we need new ones?
All right, so this is a wonderful question, and believe me, so James Webb, Hubble, and James Webb now, and there are also other telescopes like Cheops and others, the Roman telescope, they are coming, the new generations of them. But if you're looking at what's happening on the ground, right now you have giant telescopes that are being built. Some of them already in function, but in the coming years, you will have this series of 8-meter telescope, multiple mirrors. They are going to be more powerful than some of the space telescopes. And you're looking at exoplanets in many different ways. Today, you can look at these exoplanets. You can still search them through transit, through 5 different ways of detecting them. But you can also peer through their atmosphere, try and understand if you're seeing different gases and molecules that can tell you whether life is there or not. So this is the difficulty is that there is no unambiguous signature of life. The only unambiguous signature of life would be to find a synthetic molecule, for instance, or let's call it pollution, for instance. If somebody is messing with their atmosphere as we do, you're looking for disequilibria. But to answer your question, we are continuing to build new generations of telescopes in space and underground, and it's going to change everything we know again, So stay tuned, because the best is yet to come.
Thank you.
When I grow up, I want to be an astrogeologist, and I also want to be an author. So I was wondering, how do you take your scientific discoveries and put them in a book?
That's a wonderful question. Maybe I'll answer shortly. So, you know, what you do when you become a scientist, you still have to write a lot, because then you go in the field, you're, you know, collecting data, and then you have to analyze those data, and then you have to present papers. You have to write articles. Dante just published one. You have to write them. But this is a different type of writing. You're writing for scientists. It's an exercise. But then you still have, what's the story behind it, you know? And when you have several years of being a scientist, or a decade of being a scientist, your stories start to shape up. Your characters, which is the discoveries that you're making, they are, you know, getting more depth. You have a better understanding of what the story is. So the story starts to write itself, right? And you will find a way to communicate, because by that time you already will have shared with the public, like we do today, you know, your discoveries. So it will be easier to put on the paper. But I'm sure Dante has also an answer for that.
Yeah, it's a great question, and it really is about, first of all, just sharing our love for the field, right? And when you love something, you want to tell the whole world. And that's the way I feel about my science, and my colleagues feel about it. And you want to communicate that out there and say, we get a lot of joy from our work and what we do. It's inspirational and it's profound. And so for me, I'm always thinking, because I benefited from this thinking, about the next generation, those who are coming after us, and inspiring them, giving them the stories and the courage to pursue. Because people will tell you, and I've made a career out of doing things people have told me can't be done. And so it's like, you know what, great, let me show you how to do it. That's the kind of way I look at it. And I want that attitude I want to kind of convey in the books as well.
Thank you.
You know, just to finish what you were saying here, there is something, that's a principle I have in life. When people are telling me you can do it because it doesn't exist, I say, okay, I'll invent it. Go for it.
Yep.
Thank you.
Hi, I just want to thank you both for being here today and sharing your knowledge and experience. Nathalie, you already mentioned today several times how the definition of life is a working definition that we have. So I was wondering, probably this is for the both of you, when you're going out in space and taking samples, how do you decide what might be something that relates to life? And also I was wondering if the molecules that you might be finding in different locations might be different from what we have on Earth. And so are there like special types of maybe like space molecules that we found that are different but like give you the idea that they might lead to life in other places as well, or have some kind of hints to life?
So I'll take a crack at it.
Yeah, go for it.
So for trying to figure out if we have something that relates to life, astrobiologists created what we call a ladder of life detection. And this ladder has 8 rungs. And it starts with the environment, what's habitable for life, and then you go and you have to check boxes. The problem with that is, because we don't have a definition, even when you get on the top and you've checked all your boxes, you still have to apply the skepticism principle. You know, Carl Sagan's principle. And so you're still left with a question mark. So it's converging evidence. This is what we have right now. And this is, you know, how we work. The second question was about, so the closest we have right now about things that are not life, but maybe, you know, the building blocks of life. These are these organic molecules. James Webb just discovered 12-point-something billion light years away from here. So we thought that maybe this type of molecules would be created more recently than that, you know, in different generations of stars. Once you get to stars that are like the sun. In fact, we realized 2 things with James Webb. The first image just left us totally speechless, because there were a lot more galaxies than we thought, so many more stars than we thought. And then we're discovering organic molecules a lot earlier than we thought. So we have to rethink this.
That's good.
to my left.
Thank you. I was just going to ask, I mean, we've talked about the building blocks of life. We've had some questions about that and how they have been found in some of your extraterrestrial samples. We've talked about peptides. We've talked about nucleic acids. I was wondering if you found any of these peptides or nucleic acids actually linked together, or I'm sorry, amino acids or nucleic acids actually linked together into very small peptides or very small, nucleic acids, even if it's just only like a couple. Right. And then my second question was, I think you also talked about going to extreme environments on Earth, right? Like high altitudes, going to Antarctica, even if it's just to find things that are on Earth. Like for example, in the deep thermal vents, we found enzymes and bacteria that we actually use in the lab to replicate DNA, right? Like Taq DNA polymerase. And I was just wondering if any of those kind of samples that you found in extreme environments on Earth inform the work that you're doing for understanding life outside of Earth.
Okay, I'll take the first half, and then you can take the second one. So in terms of where we are with the Bennu samples, it's a tiered process. So the first one is the individual molecules, the individual amino acids, and we're still finalizing that. And then the next stage would be looking for at least a dipeptide, 2 amino acids linked together. We haven't found it yet. We haven't even found a nucleic acid. We found the nucleobase. So the purines and the pyrimidines, but we don't have the ribose and we don't have the phosphate. So we don't even have a full nucleic acid. I know we're getting into a lot of detailed chemistry here for the audience probably, but so we're finding the very simplest molecules and we're looking for how biology uses them, which is to put them into long chains. Not yet, but please stay tuned because the analyses are coming.
For the extreme environments, what we really seek out there is, well, we can go to planets, but it takes time to get there. So our best proxies are environments on Earth that look like some of the things that we want to explore. So what we do there is to go, for me, I'm going to the Andes because it's one of the best environments as an analog to Mars. The only thing that's really different is the oxygen in the air. You have a beautiful analog not only to early Mars, but to early Earth as well. And you try to understand the habitability of this environment, the type of extreme, how the different factors vary, and how life adapts to that. And then the different questions you have is, what type of life do I find there? And then what type of instrument do I need to detect that life and the biosignature, the signatures of life that it leaves behind, not only in the chemistry, but also in the sediments, in the texture of sediments, in how life modifies its environment, in the same way as the environment modifies life. So we are preparing missions going there, and this is exactly that. We are finding out what type of instruments we need, what type of exploration strategies we need, and then we apply them to the science on space missions.
Sir.
Hi, it's a real gift to have you both here. Thank you. So I have 2 questions, either answer one or the other or both. The first is, from what I hear, the supposition is that water on this planet came from asteroids, meteorites, such like that. My understanding is that the Earth is 3/4 water and roughly 3.5 billion years old. During that time of heat and transformation, is there a chemical process where hydrogen and oxygen could have come together and formed the water and the oceans? And the second question is why, and I mean no disrespect, why is it so important to find the origin of life, or is there life on other planets, to persuade Congress to spend billions of dollars in that search? Thank you.
Sure. So I'll take the first part to begin with. The Earth is covered, the surface of the Earth is 75% water, but the Earth itself is a very, very tiny fraction of water. The Earth is mostly metallic iron and nickel, which is sitting in the core, and then magnesium silicates, which make up the mantle. And then you have this thin crust And then you have an even thinner veneer of ocean water on top of it. So it would take one asteroid about 1,000 kilometers across, so a few hundred miles across, to deliver all the water that we have on Earth today. So Earth is really depleted in water relative to the bodies of the outer solar system, for example. So it's a rare thing on Earth, even though we see it and it's on our surface as a planet. It's a very low abundance compound. In terms of how it formed, early on in the solar system's history, we were a protoplanetary disk before there were planets that existed. And the temperatures there were cool enough. Not only did the hydrogen and the oxygen bond to form gaseous water like steam, but as you got farther away from the growing sun, ices formed. And ices are really abundant, as Nathalie told us, in the outer solar system. A lot of your bodies are the kinds of abundances you talked about, 75% water or more, and this were comets or fragments of coming from the outer solar system that are like that. In terms of why it's important, it's like, why is a beautiful work of art important, right? Why is a good book important? Why is, some piece of architecture that everybody comes to, why is that important? It gives meaning to our lives, right? It gives value to what we do. It helps us understand, and I always try to convey this to my students, how lucky we all are to be alive and to be conscious in this universe. It looks like it's a really rare gift. Most of what we've discovered, it's rocks and gas and plasmas and electromagnetic fields. We haven't found any other case yet, and it's early days and we're still looking, but it's so fundamental to who we are that we want to understand what is going on and what is the importance to us. So it does, we talked about spirituality. It is that fundamental connection to the nature of the universe that makes our lives worth living, and it gives value to what we do. So I think just how lucky we are, we need to appreciate that more. And a lot of the problems of your daily life don't look as bad when you have that bigger kind of cosmic picture. You're like, you know what? I may have had a bad day, right? Like flat tire, my coffee was terrible, whatever. But you know what? I'm alive, I'm aware, I'm on this beautiful planet with these beautiful people, so things aren't all that bad.
And there is also a very practical aspect to that. I'm also very inclined to the spiritual aspect of it. But I want to bring it back to the practical, because this is often time where people clash a little bit with what we're doing. And astrobiology, I often say it's not the picture, the beautiful picture you see of a planet that really matters. Yes, it matters, but that's all the technology that's behind, and that technology is being served back here on Earth in your everyday life. I often take the LASIK, for instance, the surgery for your eyes. This comes from the docking of two spacecraft, 40,000 laser measurement a second. And this is why so many people, recover their sight. Artificial limbs, heart valves, your car, GPS, etc. It's everywhere in your life. It doesn't say astrobiology on it, but it's there. It's space science, it's space exploration. The other thing is that you were talking about billions and billions and billions, not cars like stars, but dollars. Space science and exploration is 0.4% of the national budget.
How much?
0.4.
Yeah.
And frankly, when you look, I'm more for the military as well, because everybody has a function. But if I have to spend money killing people or educating people,
Okay, thank you.
We sadly have time for just one more question, and you get it.
So earlier you mentioned climate change on Venus and Mars, and I wondered why it's so frowned upon on Earth and why we're trying so hard to prevent it if it happens naturally on other planets.
That's a great question. Part of it is because it's changing our livelihood, right? It's going to start to affect agriculture and our ability to feed all the people on the Earth, right? It's going to drive a lot of migration because areas are going to become less and less habitable and people are going to start moving, and we're already seeing that, and that's driving a lot of political tension. So in terms of, as an astrobiologist and a planetary scientist who thinks on billion-year timescales, you're right. It doesn't matter because life will survive. There'll be something that makes it through. Life has gone through mass extinctions before, the dinosaurs, the end of the Permian. Life gets wiped out throughout geologic history and it bounces back. So if you only care about life, you're right, let's let it go. I think we own it because it's our actions that are driving in a very, very rapid timescale these climate changes, and it's going to make human life very difficult if we don't do something about it. So it is selfish in that sense, but I think it's in our self-interest to address it so that we can feed everybody, so that everybody can have a place to live that they're comfortable with and safe and secure. Climate change is going to disrupt a lot of that. It already is. It already is.
And also, if you want to take the responsibility of extinguishing a very biodiverse biosphere, and we are, at this point in time, taking that responsibility, and the other species don't have a voice to defend themselves. So as the apex species, we have a responsibility to make sure that we are keeping this planet, you know, as a working environment for everybody. So it's not as simple as that. It's a real tragedy right now.
Drs. Dante, Lauretta, and Nathalie Cabrol will be signing their books. Thank you so much.